Right, so today I'm just going to, obviously one can't cover the whole topic of every geophysical technique for diamonds in detail. So what I've done is I've given a couple of these talks before, and I've thrown out all of the introductory stuff, assuming that everybody knows something about geophysics already, and I'm just going to sort of whiz through anything like that, and then get into the juicier stuff of some real case studies and also new developments, which I think everyone is interested to see because of the whole drone thing, radar, AMT, techniques that we're not that used to. We're all used to these techniques here, magnetics, which is by far the most common and important for anyone doing any kind of exploration. But then we've also been, with magnetics goes the radiometric stuff, gamma ray spectrometry, and then we've also often used gravity in the past and some EM. But the newer stuff, the AMT, drone, UAV platform, plus radar, and to some extent geophysical logging. It's been around a long time, geophysical logging, but I'll just run through that stuff again because occasionally we've done something innovative there. So if I just quickly remind you about the Earth's magnetic field, the only critical thing to remember really is that the field comes out vertically at the poles and it's horizontal at the equator. And a lot of people lose track of that, and they go, well, why is it not a dipole? Why is it different? Why is it, why is it a high, et cetera, et cetera? You have to know your latitude. The big thing with magnetic field is, depending on your latitude, the magnetic body, a magnetic anomaly of any body looks totally different at the equator because it's horizontal, and at the poles because the field is coming out vertically. So just to brush up on magnetic susceptibility, this is the ability of any material to enhance applied magnetic field. So in our case, we have a magnetite grain, and within magnetite grains in any rock, there are domains. They're either small or they're large. And what happens is we apply the Earth's external field, this applied field, and that magnetic domain either enhances it or subtracts from it or does something to it. So we get an addition of the field or a subtraction of the field, depending on whether these domains are superparamagnetic or magnetic, etc. Just remember that not all minerals do have a magnetic susceptibility. The most susceptible minerals are generally oxides, although some sulfides are as well. And I'll draw your attention to magnetite over here. We're talking SI units here. Magnetite is by far and away, with titanium maghemite, the mineral most responsible for any kind of response to the Earth's magnetic field, any kind of magnetic response. But if you look at this guy here, this is what's critical when it comes to kimberlites. And you'll see that it can actually go right up into the magnetite field and the maghemite field. Into the millions, 3.8 million. So a lot of people overlook the fact that ilmenite can be, in fact, very susceptible, and it can also not be susceptible. It can be very low. So that's the problem with kimberlites. Some of them are highly visible in magnetic fields or in a magnetic survey, and some of them are not. And that all depends on the iron content and many, many other factors. But ilmenite is the mineral that we're looking at, really, not magnetite. I'm just going to run into some filters quickly and show you the effects, because a lot of people know what mag is and what a kimberlite looks like in a magnetic survey, but don't fully understand what it is when we do with these filters. So I'll just remind you, normal polarization in southern Africa at this latitude, which is around 30 degrees south, sort of in the subtropics, we have a normal dipole, where the high is to the north and the magnetic low is to the south. However, often we have some remnants thrown in there, and the remnants is caused by usually some magnetite in the rock, and it has a memory of where it was when this rock was injected, and that can become quite useful. So if we reduce this to the pole, i.e. we're no longer hot at this latitude, but we're at one of the poles, we should just see a big round red blob. But actually, in this particular case of a kimberlite pipe, I reduced to the pole and the low is still showing strongly. That's a very quick test for remnants. If the low is still showing strongly after you've done reduction to the pole, then you can immediately say that you do have remnants. So that's one little trick. Let's look at other effects of filters. If we look at these three bodies here, these are not necessarily kimbolites, but they are three dipoles. And it's quite good to show these because you see here we have a perfect normal dipole. And then you have these other weird little guys that generally would say, oh, they're dolerite or something else. And then something that looks like it's attached to a big sill, but the low is giving it away. I'm just going to show you the effect of running spatial filters on these. This is the total field. So what we do if we reduce to the pole, we put the high directly over the body, and if there's no remnants, there's no low left. So you can see that there's just tiny little lows here. You could basically write them off. So you could say that these bodies are not exactly remnantly polarized. They're fine. And what's happened is we've managed to move the high slightly south. I'll just show you the previous slide again. The high actually moves south towards the midpoint between the high and the low. And it puts the high directly over the body, which is why everybody loves it so much. The problem with this is that when you get to the equator, reduction to the pole does not work that well. We tend to blow up north-south features and becomes very unstable because we are rapidly approaching 0 degrees and we're doing trig with 0 degrees. So you've got to be aware that close to the equator, reduction to the pole is not the best thing you should do. It works best at high latitudes. Vertical derivatives basically sharpen up everything. So if I go back to this previous, you'll see that this magnetic texture in the background here, this ripple effect, is not as obvious as it is when I sharpen it up with the derivative. And also, you'll find that when you do TMI, total field, and reduction to the pole, these magnetic highs are much bigger than the body. What first vertical derivative tends to do is make them smaller and put them and create an anomaly that is more in keeping with the size of the body that's causing it. You'll see this is first vertical derivative of the TMI, so we still have the low, and you'll see how much sharper everything's become, how much smaller, and then also this ripple texture, which is the background geology, is showing up much more clearly. And even more so if I do a second vertical derivative, this really breaks the body up into its component parts. You can see that some of these were in fact lobate or two bodies, very narrow features popping out. And what's lovely about this second vertical derivative when you have good mag is you can now do geological mapping quite sharply. It pulls out these contacts very well, and I can say with confidence that to the right of this line, where magnetically it's quite smooth, and to the left of that line, that's a geological contact, because I have this very strong texture over what may be a dolerite or gabbro here, and then I have some sort of sediment there, and you can see a tongue of that coming in. So they sharpen things up. And when you look at analytical signal, which everybody has heard of, and we always do when we're looking for kimberlite pipes as well, what it does is it cuts through the clutter. Previously, everything was quite noisy and difficult to keep your eye on any one thing that might be a kimberlite. But when we do analytical signal, it tends to show the most magnetic features on the map. It puts a big red blob over them, which we all love. And also it puts it directly, the anomaly directly over the body, just like reduction to the pole. It just works on gradients. So an analytical signal in a busy terrain can often help your eye adjust to the noise. You can adjust the colors, get rid of all the background noise, and say, okay, I only want to see the most magnetic things in my magnetic map. And that's what it's done here. When I show you what it does in profile, so say now we are looking at a line of magnetic data in profile, and this is your kimberlite down here in yellow. When we reduce to the pole or do a magnetic signal, analytical signal, we have originally at this latitude in Southern Africa, we have a low and a high, and you'll see the body is positioned somewhere between the low and the high, usually a little bit south of the high. But what happens when we reduce to the pole or the analytical signal, it removes this dipole, gets rid of the low, and the black curve now shows you a nice high, only a high directly over the body. That applies to both reduction to the pole and analytical signal. In section, when we do a vertical derivative of the TMI, it just sharpens it up, moves the low closer and the high more in keeping with the size of the body. And it basically tightens up, so you can say between the high and the low, And in this case, on top where the high is, so we've shifted the high a little bit south, is more or less where my body is. I've got a much more accurate idea of where this body is and what its size is, rather than having this spread out red curve. I've now got this much tighter black curve. And of course, we can also now do 3D modeling of kimberlitic bodies or dipoles. So if this is my magnetic dipole that was recorded in the ground magnetic survey on the top left here, there's something now that Geophysical supplies called voxy modeling, which is named after the voxel, the volume element, as opposed to a pixel, which is a picture element. So what it does is it puts a volume beneath the survey in the Earth, and it has millions and millions of little cubes, and it gives each cube a magnetic susceptibility. And it says, okay, how do I have to vary the magnetic susceptibility of each and every cube in this volume of space beneath the survey until I've got a closed volumetric area that on its own, when I clip it down to the highest magnetic susceptibility values, that will explain that magnetic anomaly. And you can actually generate the field again from this body and compare them directly. So you have the measured field from the magnetometer, you have the generated field from the model, and you can see that the two would be identical. If not, you've got a slight error, but it's never going to be perfect. But at least you can say, well, this body pretty much generates that dipolar anomaly over there. That's what my body looks like at depth. And I can measure, of course, how deep it is, how large it is, can even create its measure its volume. Of course, this has problems. We don't know anything about the size or the depth of the body at the time we're usually working with it. So we have to decide what magnetic susceptibility level to clip in the voxel. And depending on what level you clip it at, you either have a bigger body that's shallower or you have a smaller body that's deeper. And that is always the conundrum with geophysics. So that's just to brush you up again on magnetic stuff, so we can move on to the drones themselves. Basically, a drone is just a kind of a nickname for an unmanned aerial vehicle, a UAV. Most people prefer that name, but throughout I'm just going to use the word drone because we use the slang. And essentially what you're doing now is you do have fixed wing drones, but in general for this kind of thing we use hexacopter drones. So they have 6 blades, and we sling a magnetometer up to 3 meters below them, because obviously it's an incredibly sensitive piece of equipment and you can't have the whirling blades or anything metallic in the drone itself affecting the magnetometer. There's been some great new breakthroughs in terms of magnetometers too. We used to have those things the size of a beer mug, cesium vapor magnetometers that we all grew up on. But now what we're using is what is called an MFAM, which is a microfabricated atomic magnetometer. And you're looking at it here where my mouse is. That's a 5 Rand coin. So this tiny little brick, not much bigger than a 5 Rand coin, is now what we call the magnetometer inside some of these birds. You don't have to have it in an aerodynamic bird. You could literally hang that thing on a string, but it's much better to know the orientation first of all, so that you keep the nose of this bird, this geometrics bird, along the line direction. Because like most magnetometers, they're actually sensitive to the direction that the field is passing through them. And in addition, we have 2 of them in here. We can have one at one orientation and one at another orientation, and therefore when we flip the drone around, we can pick up the magnetic field more accurately with one of them, one on the other. We can take an average, or we can say, right, we've got a better result from this drone in that orientation. Or you can just have them both in the same orientation. We've got no issues with the field inclination. And you can either average them or use the one as a backup. And what we find is fantastic is that the one is a backup. So if ever anything goes wrong and one of these little guys is spiking, it tends to serendipitously happen that the other one is working well on that day. It's very seldom that both of them give problems on the same day. And even better, you can, as I say, take the average of the 2 and get a really accurate result. So this bird that we use is called the Geometrics Mag Arrow. It has 2 MFAMs inside it, which you can orientate. And we sling it with its nose forward in front of the drone, below the drone, about 3 meters below the drone, on nylon string. And the remarkable thing about this bird, this magnetometer, is that it takes a reading we used to take a reading every second. What we considered a really good rate of sampling was 1 every second. And then when we started really good airborne platforms, we used to take 20 readings a second and consider that fantastic. So that's 20 hertz. This little guy samples 1,000 times per second. So every second we are getting 1,000 readings, and that's because of the new design of these MFAMs. They work on an optically pumped laser system, and they can take this many readings in a second. What's fantastic about that is, of course, you can pick up every tiny little blip along the flight path, but also you can do electromagnetics. You are basically sampling the B field of an electromagnetic response, i.e. the magnetic field extreme blip in the magnetic field when you energize something with an electromagnetic field. So what these new magnetometers are doing, and this is where things get exciting, is that they're allowing us to do electromagnetic surveys by sampling the B field with a magnetometer. All we have to do is lay the loop on the ground, energize whatever's in the ground. We don't know what's there. We fly what is, after all, just a mag survey. And if we're clever, we can sample the B field out of that in very, very early times. And this has only become available of late because we are now able to sample the magnetic field so rapidly. Okay, why would we do drone surveys? Well, they fit in somewhere between ground mag surveys and aircraft surveys. And the reason is that companies like Excalibur, NRG, all the airborne companies, they won't mobilize for a small survey. They basically say it's too small, we're not interested. And there are certain sizes of surveys that fit in there, right in between the ground survey size and the airborne survey, the aeroplane survey size, where drones fit in just nicely. So they fill a gap. Some ground surveys are in very, very difficult areas. They're just too large to do quickly. They're mountainous, they're full of thorns or forest or swamp, choose your pick, out at sea. You can't do ground surveys, but they're too small for an aircraft to take them on. So they fit in very neatly in this gap. They can work in very rough terrain, and we can do about 10 times as much as a ground survey. So it's quite a lot less than an aircraft would do. So Excalibur would do 700 Ks in a day. We can do at the moment about 100 kilometers in a day, but that's 10 times more than you can do on the ground. So as you can see, even with that, the drone survey is fitting in right in the middle. And they're good for terrain where it's too tough to do it easily on the ground. So say, for example, you're in Angola and you've got guys working alluvial gravels and it's dangerous. They don't want you messing around. They don't want you walking in amongst their mining operation. You can fly a drone over and hopefully they won't throw sticks and stones at it. And we're currently flying a drone survey in Swaziland where the kids have been throwing sticks and stones at the drone the whole time as it goes over. So you do need community liaison where you can get it. Okay, so that's why we do it. Why only magnetics? At the moment, it's not only magnetic. It's just that magnetics was the quickest, the easiest, and the lightest bird to manufacture. Electromagnetics, radiometrics, things like that are heavy. And when we're using hexacopter drones, we can only take so much payload, as they call it, anywhere from 1 kilogram to 5 kilograms if it's a big drone. So we just can't carry what an aircraft can carry, unless you use a bigger and bigger and bigger drone, and eventually you're basically using an aircraft. So somewhere there's a cutoff in the size. But MAG was, because it's such a popular thing, MAG was one of the first to go, as well as first to be miniaturized enough to be used like this. And obviously there's cameras as well. I'll get into the cameras now. So here's a quick example of a drone survey we flew. This is looking for kimberlites somewhere in South Africa. This area is about 2.5 kilometers long by 1.5 kilometers wide, and was full of culture. There were lots of power lines. That's what these white caps are. Farmhouses, mines, all sorts of nonsense. One of the great things about a drone is it gets you 20 meters off the ground or 10 meters off the ground, and it kind of filters out cultural noise. So for example, if I had to walk with a magnetometer in amongst an operating mine, I would get a lot of electrical noise. I'd pick up every truck, I'd pick up every shed. But I can actually say, well, in this particular case on this survey, I want to fly about 20, 30 meters up. And just above these power lines, I'll cut out the noise from the power lines. And then I will filter out most of the buildings and most of the muck from the culture. And in a way, that's my first level of filtration, upward continuing, if you like, from a ground survey. The speed comes in here. 2.5 Ks by 1 Ks. Took us less than a day to fly this, 1 day to interpret it. And voila, you have your answer. Well, there's your kimberlite pipe. And there are a whole bunch of what we think are dikes coming through here, kimberlite dikes, which we could tell as different from all the dolerites in the area. Let me just go back. We said this is dolerite. That's a dolerite dike. This is probably a sill. There's some response from a sill here. That all just comes down to interpretation. But the bottom line is that within 2 days of putting the drone out there, you have fully fledged interpretation, the whole thing done, filtered, the lot. So it's much faster than a ground survey and it's less noisy. So that's an example of a real-life survey. What about the cameras, the LiDAR, the altimeters, the hyperspectral, all of that? Okay, here's an example of what we do with LiDAR on a drone. LiDAR are usually quite expensive. If you do it with an aircraft, much cheaper with a drone. What we can do is we now measure with the laser. LiDAR is laser interferometry, basically. This laser fires, again, something like 20,000 times a second, and it picks up every little blip in the terrain. So here we're doing a digital terrain model, essentially, but it can fire through leaves because it fires so often, goes right through the leaves of the trees and everything, maps the ground. And then afterwards, because we're flying with a camera at the same time, we can essentially plaster the true color, the RGB coloring, on top of the relief. So now we have a 3-dimensional look at our landscape where every tree and every building and every little digging and of course the workings, they all have a 3-dimensionality to them, and we can view them in 3D. I'll show you that now. But also we can put natural color onto them. So essentially, it's as if you're sitting on the drone looking down at it and you're seeing everything in color. We can also use reflectivity coloration on a LiDAR survey. So again, we have the digital terrain model, which is accurate to 1 or 2 centimeters. But we can say, right, the most reflective stuff will be red, the least reflective stuff will be blue, and everything in between. And sometimes that helps us filter out, say, the vegetation. Anything that's dark in this might be vegetation. Anything that's brightly colored in red may be what we're looking for, which could be silt or diamond digging in this case. And then what it's really useful for is measuring how much material has come out of the pit and how much material is standing in the tailings, or sorry, standing in the dumps. So every week, guys take stuff out of a pit and they plonk it on a dump as a sort of a, which they're going to access later. And by flying a LiDAR survey every week with a drone, you can literally say how much material came out of the pit and how much is now sitting on the dump. And you can view it all in 3D, and you can put the RGB coloring onto it. So you have your trees in natural color and you have the soil in natural color. So a lot of people like Palabora, for example, want to know how much magnetite is sitting in a dump and how much has been taken out by a truck and how much is added onto this dump, how much has been subtracted. You do a 1 centimeter accurate LiDAR survey every week, and every week you can say, well, the dump size reduced by this many centimeters cubed. So that's how much has been taken off the dump, and this is how much has been taken out of the pit and added to that dump. So what are the problems of drones? Is we have a line of sight rule and therefore limited range. Basically, most countries tell you that you have to be able to see the drone at any one point, so that if it goes down, you can see where it went down. It's a bit of a ridiculous rule, and we get away from it by putting ourselves up on a hill and using binoculars, or excuse me, you can literally put spotters out in your survey area or build platforms. Usually we try and use copies and try and view the drone that way. But it is a pain, particularly if you're in a flat area. Say you're in Botswana, you can only really see that drone for, if you're lucky, a couple of 100 meters at a time. So then you have to build a platform in the area, or it's just not realistic to fly 500 meters at a time. You want to try and fly blocks with a drone of 2 kilometers by 1 kilometer wide and then merge all the blocks together, something like that. It's also slow compared to an aircraft in terms of not speed, but production. So we can really do about 100 kilometers per day. Ground mag is about 10 kilometers per day. And using an aircraft like a crop sprayer, you could get up to 500 kilometers a day, even 700. So again, you can see we're right in between the ground mag survey and the aircraft survey there. Power lines and trees are a problem. We have smacked trees in Angola, and we have put our drone and our bird into power lines. So one of the things you have to do before you do anything is fly a very accurate digital terrain model with LiDAR. Create your own digital terrain. In the software, tell it that it must drape this by 25 meters, which is the highest tree in the area, or you can use obstacle avoidance, which has forward-looking cameras. And when the drone sees something coming up like a tree, theoretically, it's able to go around it. But in practice, it doesn't always work. Power lines are a bit of a nightmare because you tend to catch the strings of the bird. The bird goes under, the drone goes over, and the strings go straight in. So we have nuked our drone a couple of times like that, and nobody will insure these things. It's literally impossible to get insurance. We have cross-border issues. Most governments want to pounce on drone surveys and say that they want to make money out of them, and then they start demanding civil aviation and military permits and blah, blah, blah. The whole thing becomes a nightmare of crossing borders. So drone surveys are not everything they're cracked up to be. We do have problems, lots of problems. And paperwork with pilots. Pilots have to be qualified. They have to do regular tests and pay money towards those tests. They have to have their paperwork with them, etc., etc. And you have to get permits whenever you fly a survey, particularly if you're near a military base or near an airport. Most countries will tell you may not be within 50 kilometers of an airport and maybe even 100 kilometers from a military base. And of course, the military loves to throw its weight around. They immediately ask you, do you know where the military bases are? You say, of course, I don't know where they are. They're all secret. And then they crap on you because you don't know where the military bases are. And then you have problems with the local population. Some of them get a bit upset when you're flying over with drones. Sometimes they throw things at them. Sometimes they try and shoot them down. One of the problems is, of course, that people associate drones with military activity, thanks to the US of A using drones to launch missiles, etc. Luckily, hexacopter drones don't look anything like their fixed-wing counterparts. One of the reasons we prefer hexacopter drones is that fixed-wing drones look very military, and hexacopter drones look more like toys, like the. So there are lots and lots of issues. And one of the problems is, of course, the weight of the instruments. You need a really big drone to lift 5 kilograms. So if I look at the drone developments that we're getting into now, of course, we're going to see a massive explosion in developments because everybody's starting to use these for various things. What we need is longer range. At the moment, we're using lithium polymer batteries, and you've got to have about 30 of them in the field, and you have to recharge them every 30 minutes. You have to have a full-on bucky there with fans and fridges and recharging facilities and shade and everything. And these batteries are like 2,500 Rand each. So you have to have a massive investment in batteries and be charging all the time and bringing the drone back to base after every half an hour, put new batteries in, take off you go. So then your issue is, can we use a hybrid fuel? Can we use fuel? Or can we use a hybrid which is using fuel and batteries? Problem with that is we have even more issues with fuel because governments fear that when the drone crashes, that the fuel is going to explode and you're going to start a fire. And if that's in an urban area, then you have massive problems. So we're looking rather at better, longer life and lighter batteries. And as we all know, that's happening all the time. We try cobalt, we try vanadium, we try lithium, and we just keep going. The other thing that's happening is we're getting tiny crystal packs made for radiometrics. Normally, crystal packs are very heavy. The sort of weight of a crystal pack you'd put in a normal aircraft for a MagRad survey is about 30 kgs. There's no ways you can carry that around with standard sort of drones, but up to 5 kilograms maybe. We're starting to make crystal packs that come in very light, about 3 kgs. But the problem with those is they're not very good because the way it works with gamma rays is the bigger your surface area, the more accurate radiometric survey is. So that's in its infancy. We're going to get there as always. Most exciting thing I think that's happening is the B-field EM surveys using a loop on the ground and your fast sampling magnetometer. We're getting magnetometers, funny enough, it's ironic, but they're starting to use diamond magnetic sensors, diamond-based sensors, and they reckon they're going to sample at 20,000 hertz and even more. So we really are going to be able to start doing EM surveys with drones simply by flying a magnetometer. And if you tell me that you think your sulfides or whatever it is of interest are in this field, we just energize that with a loop and then we fly over it with a drone just like a mag survey. We're also getting electromagnetic and resistivity sensors miniaturized for drones. That's happening at the moment. I'm going to show you what one looks like. It's like something out of Star Wars. And then, of course, we're getting not just the LiDAR and the color cameras, but the multi and hyperspectral surveys using cameras in the shortwave infrared band and thermal bands, etc. So you can basically buy these things as cameras online. You can buy a hyperspectral camera online, put it on a drone, take a whole bunch of photographs, send it to Neil Pendog for processing. So all of this can be done. This is what a new EM, small EM system is looking like. It truly is something out of Star Wars. There's a little loop on the bottom there. We have magnetic sensors. It's looking crazy. And obviously we can go much bigger than this. We can go to really big drones and then carry something slightly bigger than that. I'll show you what an AMT sensor looks like shortly, and then you'll see the kind of way we're going. We're making up small darts that can go beneath a drone like this. So say maybe no longer than a meter long, maybe 3 kilograms in size. So all sorts of developments in the drone world. Right, it's half an hour down. Just going to move on to some gravity quickly. Essentially, gravity plays a big role in diamond exploration simply because when we're in magnetic background, gravity's or EM is our next call to how can we spot a kimberlite. We use a differential GPS usually, and we use a Citrix gravimeter that looks something like that. And basically it works on the principle that two masses attract each other. Essentially the mass of rock beneath the gravimeter attracts a mass within the gravimeter, which is sitting inside a vacuum, which is super cooled sometimes, or just in a vacuum. It attracts it downwards if the rock is dense, or it lets it go up a little bit if the rock is not as dense as the background. So what does a gravimeter measure? It's essentially the gravitational attraction of the rock directly beneath it. Gravimeters are sensitive to variations of 1 part in 100 million, which is less than 10 ppb. So they're extremely sensitive instruments and very expensive. And in order for this to work, we need to know our relative elevation or our exact elevation to 2 to 3 centimeters. So huge steps were made the days when satellites started putting out accurate corrections to elevation. So we now use differential GPS radio. So we use GPS as the theodolite, if you like, and we use a correction from a base station or the dumpy level. So essentially it's all done with GPS, which is another great technological advancement. Why would you use gravity? Well, sometimes you have a magnetic background that is very, very busy and you can't spot your kimberlitic dipoles in it. That happens very often. For example, the mobile belt. Sometimes you want to confirm the size of a kimberlitic body. Sometimes only certain facies of a kimberlite are magnetic, and others are not so magnetic. So you get different pulses of magma. They don't have as much ilmenite. Maybe there's not as much iron in the ilmenite. So you have varying magnetic response across any given kimberlite. And by doing another kind of survey, like an EM survey or a gravity survey, we can come up with several sizes for the body and then average it, for example. You may suspect non-magnetic kimberlites. Group 2 kimberlites don't have a lot of ilmenite in them. They're very micaceous, and therefore you can fly an extremely sensitive magnetic survey in a quiet background and still not see them. I'm going to show you some examples of that from Angola. Note that a gravity survey is slow, and to cover a large area, it takes a lot of time. Airborne gravity is getting better each year, and we know that De Beers used a Zeppelin, and we know that you can now fly airborne gravity gradiometry with aircraft platforms, and it's starting to be used quite a lot in kimberlite exploration. The issue has always been the difficulty in measuring the aircraft movement accurately, because that's an acceleration, and the gravitational force is essentially acceleration. So you have to know exactly what your aircraft is doing. Hence, we use the gradients. It's much easier to work with gradients than total field. Simplified density structure of a kimberlite pipe is generally that the top 30 meters or so in any given weathered terrain is less dense than the main body of the kimberlite beneath it, because it's weathered. So essentially we get yellow ground or crater facies on top. The density is down at approximately 2.3 grams per cc, and often the main body of the kimberlite, I'm sure we don't use these terms anymore. I've been out of De Beers for a while, but what we used to call TKB or hyperbissal kimberlite, is often more like 2.5 to 2.8 grams per cc. So we're looking for a little gentle density low on top of the kimberlite pipe. And if this is, say, quartzite, which is 2.7, it's going to stand out nicely as a low. So this is what we're expecting to see. Gravity profile comes in. You'll see how much bigger this gravity low is than the body. Really, the kimberlite sits in the middle, and we start getting a decrease on the sides. So again, we're going to have to do some fancy filtering to get a more accurate idea of the actual size. Some notes: if the density of the country rock is very low, the pipe can actually show, the kimberlite pipe can actually show the gravity high. So it's essential to know what your background geology is, have a good handle on what its density might be. We're looking at a relative contrast, so you have to be aware of the surrounding geology. Here's an example from some kimberlites in Botswana, where you can see these two tiny little dipolar features here. So we're quite happy that these are magnetic dipoles and then maybe kimberlites. Now, maybe with gravity, we can tell which is a kimberlite and which is dolerite. You can see there is a lot of dolerite sill activity in the area. That's what all this other muck is in the background. First of all, I do a derivative on my magnetics. That tightens everything up. I see they're both nice little dipoles, but they look quite different. This one is more of a high. This one has a strong low. So what is that telling me? Well, let's do a gravity survey and see. If I just do a total field gravity, Brugger gravity here, you can see how strongly it's picked up this huge doleritic body here, and this one here, the sill. And even in the total field, I can see there's a bit of a low, a little depression over that body, but nothing over that one. If anything, there's a slight high. If I just did, for example, a derivative to sharpen that up, or a residual, I would immediately see that there's a nice low over that body, and there's nothing over that body. So immediately I've discriminated between these two bodies. I'm thinking that this one is a kimberlite and that that one is not. I may be wrong. I mean, you may actually have two kinds of kimberlite in any given province. There's a big structure separating these two anyway. But my first indication as a prioritization tool is that the one with the gravity low on it is some sort of crater facies or weathered kimberlite, and this one is more likely to be doleritic. There's an example in Angola where in the total field magnetics, we don't have a classic dipole. We just have this strange looking magnetic high. I would not normally go for that as a kimberlitic target. Same with these things here. We don't really have strong lows with them. Don't like it. And you get a lot of this, a lot of monopolar highs. We're not sure what they are. There's lots of dolerite in the area. There's lots of other muck. But in this case, indicator grains were telling us that this may be something. Let's do a gravity survey over it. And immediately we see this beautiful, strong gravity low. Drill two boreholes, and this one intersects a kimberlite. So it's a good discriminatory tool, and it's a good prioritization tool, and it's good for deciding whether you should drill something when you're not sure, or you may have lots of drill targets. So gravity is definitely a very, very powerful tool in our arsenal when it comes to kimberlite prospecting. Sometimes we have gravity highs and lows over a cluster of kimberlites. And the reason for that is that kimberlites pick up country rock. So when they intruded, they can sometimes pick up massive xenoliths of the country rock. That's something else to be aware of. So in this case, this is a kimberlite pipe. It's got a strong gravity high over it. It happens to be full of basalt, which is what the rest of this is. These two little kimberlites here in the cluster, these are all kimberlites, are little gravity lows, and those two are gravity highs. So it all depends on sometimes not only what the background is, but whether they picked up large blocks of xenolith. So you've got to be very careful. As always, geophysics, nothing is cut and dried. It's more of an art than a science, and experience counts for everything. You need to go, wow, I've seen this before. I've seen kimberlites that are highs and lows in some backgrounds. So that's gravity for you. And of course, now with Voxy again, we can do some potential field, just like magnetics. We can do 3D, three-dimensional modeling, and we can come up with bodies that start to look surprisingly realistic in terms of kimberlitic formation or kimberlite formation. In this case, the gravity has managed to split this kimberlite into two bodies and even two separate lobes. And we start to get an idea of what it might look like at depth. Of course, potential fields are not very good at modeling at depth or with depth extent, but it is a start, and you can use this to direct your drilling. Okay, moving swiftly along onto EM because we're running out of time. We've got 20 minutes left. Basically, with EM, we measure conductivity. Connected conductors give the strongest response. Generally best for metallic substances, things like sulfides, pyrite, etc. But in resistive terrain, weak conductors such as kimberlite can sometimes be seen with EM, and that's what we work towards. They're generally very weak conductors. But if the ground is very, very resistive, for example, in Canada, where you've got glaciated granitic terrain, then your kimberlites stand out nicely. And the reason they do that is because they have weathered ground. They have clays on top because they're weathered. When would you use them? Magnetic background, again, very busy. Can't see my kimberlites because the mag is so busy. Again, I want to confirm the size of a body, or I want to detect, in the case of alluvials, the clay layers. Sometimes clay layers are useful when you're mining alluvials. Sometimes there's a clay layer just above what you're interested in terms of your gravel, or even within your gravel. Therefore, EM becomes quite a useful tool in mapping your channels. So channel mapping. And again, when you suspect there are non-magnetic kimberlites present in an area, I'm going to show you a good example from Angola. Note that EM is quite expensive. It's more advanced. It's not as expensive as an airborne gravity survey, but it's a lot more expensive than an airborne magnetic survey. So as always, everything's relative. Can I afford to fly an EM survey? Can I afford to fly a gravity survey? If not, then I've got to do it on the ground, but I can't cover a lot of ground. So these things, everything's an interplay. It all depends on budgets. Basics of EM is essentially we fly over the ground, we pump a primary field into the ground, we turn it off, and then we have a receiver, and we measure the secondary field coming back from anything conductive. So we've set up an eddy current in this body. It creates a secondary field. We turn off this primary field quickly. We're talking about milliseconds, microseconds, and the receiver picks up the secondary field coming from that body. So we pump it into the ground, and then we get that guy coming back. Only reason it works sometimes over kimberlites is for the same reason it works over gravity sometimes. Nothing is a golden rule. Sometimes it works, sometimes it doesn't. Essentially, we have conductive weathered ground again, and we get serpentinized clays in here. And it's the formation of clay, essentially, that gives us free ions, which are therefore running in the ground, will run in the ground like electrons, and therefore we have a weak conductor over some kimberlites. Sometimes we have crater facies over a kimberlite, and there are clays in the crater facies. So it all comes down to where are you and what sort of kimberlites do you have. Here's an example of 2 or 3 in Angola. These are magnetic dipoles. Looking at total field airborne magnetics here. There's a dipole, there's a dipole, there's a dipole, there's a dipole. But over here, there's nothing. We fly EM over that area. Just remember what this looks like and where that X is. And lo and behold, we pick up that magnetic dipole. But if I go back to this guy, you'll see there was just about nothing there in the mag. This is a good example of where we picked up magnetic facies of a pipe, elongated pipe, and there are the magnetic facies. But over here, we have a totally non-magnetic facies. And thanks to the EM, we're able to put a hole in there and say, wow, this pipe's much bigger than that mag body. In fact, the bulk of it is over here. In this case, probably crater. If you look at these 5 magnetic anomalies, they're all very, very different. This one you can hardly see. It's almost a texture. That's a classic dipole. It's a classic dipole. These are small dipoles. That's the total magnetic field. We fly over this area with EM. And, sorry, before I show you the EM, this is a horizontal gradient of the magnetics. Great thing about the horizontal gradient is it highlights the circular nature of the body. And in this case, in this area in Angola, it actually shows us multiple lobes. There are 3 sort of lobes of this guy. And sometimes in just one of these dipoles, we'll have, it looks like an outer crater and then something in the center. This guy just something in the center, maybe something out in the outer zone. So horizontal gradient is a very good filter in certain areas where you're looking for kimberlites. If I now fly the EM, and this is channel 25, so it's just one of the time gates, we're picking up the rivers very, very strongly. So all these rivers have clays in them, and essentially what you're looking at here is almost a topographic map, except that some of these bodies have lovely circular features on them. And you'll see there's an electromagnetic response in a circle, a donut, around this body, but it's more resistive in the center. So what it's telling me is that we seem to have some sort of a conductive outer rim or crater, and then with at the center of this body, it's resistive. So maybe that's the kimberlite. These guys don't show at all. This guy's saying, heck, well, I've just got a bit of river sediment on top of me. That one shows a little bit of an electromagnetic high. This one shows two circular features with a river going through the middle. So you've got a host of different responses, just like you did in the mag. It's so useful to be able to view everything. Mag, EM, tau, channels, everything. We've got so many different responses. When I look at later channels, when I look at tau, which is the decay constant, and I can look at it for just say 6 channels. This is time gate 19 to 21 on the SkyTem system. You'll see that I've picked up the circular nature of that big body. Here I've picked up the central core there, which was a river, a body with a river going through it. I'm now getting a hint that there's something circular there, maybe a hint there, but essentially nothing, and then a river just passing through there. So again, 5 different responses. Well, let me just go back.
Gavin, you've got 15 minutes.
Okay, I'll just have to speed it up a little bit. So basically what this is showing you is that EM can detect different kinds of kimberlites, different kinds of fascies, and totally different responses on different kinds of kimberlite. And by the interplay of the magnetics, the decay constant, and the different time gates, it becomes very useful. AMT, so this is something that is becoming more and more used throughout the exploration industry, audiomagnetic tellurics. It's basically a deep-seeing electromagnetic technique with the added benefit is that we don't need a transmitter. It basically measures the weak currents in the crust from lightning strikes. And a lot of these lightning strikes are up at the equator, say in Africa. All year round, we get lightning strikes at the equator, and then these very weak telluric currents come cruising back through the crust all the way down south or all the way up north. And we pick those up by listening with cables and with magnetometers for at least 20 minutes at any one point. And then we come up with ratios that show us the conductivity of the Earth beneath us. Essentially, it's a deep-seeing electromagnetic technique with the added bonus that we don't need a transmitter. Lightning strikes on a transmitter. And this is it's not a new technique, but it's a technique that is being used more and more for kimberlites and indeed even for alluvial. Here's an example of a basalt layer in Botswana, where AMT, or in this case, controlled source electromagnetic tellurics was used. Controlled source means we actually put a cable in at infinity, so you can, in fact, add to the current. If there's very weak telluric currents, you can add, but we don't always do that. Often we don't. And you'll see there's a hole in the basalt here. So we're measuring resistive basalt, resistive basalt, resistive basalt. Suddenly there's a hole, and then more resistive basalt. And this is telling us where this kimberlite body is, and it's also showing us that there's shale or something more conductive, possibly even an aquifer beneath the basalt. Here's an example of the Regis kimberlite in Brazil, where an AMT section is done over the body. It's starting to show us, okay, now what we've done in this case is AMT essentially measures resistivity, not conductivity. So what we need to do is just flip it around. It's the inverse of resistivity. So all we do really in this image is we make the low resistivity values red, the hot colors, and the high resistivity values become the blue colors. So in other words, the kimberlite is more conductive than its surroundings. And that's what the Regis kimberlite looks like in section. But if you do multiple sections and you add them all together, you can do some very clever 3D modeling. And in fact, once you have it in this 3D shape, you can cut and slice and dice, just like you can with the other techniques I showed you in Boxy. You can slice and dice this kimberlite pipe, and you get something that looks quite kimberlitic, tapering off to a root down there. Because AMT is our deepest seeing technique, it can see down about 1 kilometer quite easily. The reason for that is we don't have to put the current down there. It's coming from the equator as lightning strikes or a nearby thunderstorm as a lightning strike, and it's automatically very deep. It's already 1 kilometer down. That's the beauty of AMT. Just by changing the frequency we listen at, we can convert it to depth. So we can image, theoretically, a kimberlite pipe like this Regis kimberlite pipe in Brazil. We can image it in 3D down to, in this case, this is 800 meters. And you can slice that, you can slice through it, and you can see we're getting a very realistic crater shape out of this AMT. We can slice it in plan, and we can view it in 3D, spin it around, and you'll see that down to the first few hundred meters, we're getting a very nice crater shape. classic champagne glass. So AMT is becoming massive. And I do know that there have been some very nice studies for masters and things to do with De Beers that unfortunately I wasn't allowed to show, that trialed numerous AMT techniques, because there are various ways of doing AMT, over a bunch of kimberlites in Botswana. And that paper should be coming out sometime. When it does, we'll look forward to it with anticipation, because some of the techniques managed to image these bodies in Botswana down to great depth. Mobile MT and Z10. Okay, these are the kind of birds the guys are making. Then these are flown from helicopters at the moment. This is becoming very popular. People are now flying AMT from the air. You can either measure the magnetic field, or you can measure the electromagnetic field from these telluric currents, or both. And what you do is you measure them in the X, Y, and Z direction. That's why the bird is so round, because it has coils in 3 different planes, just like we sometimes do with EM. And you have base stations. You have something on the ground that measures the telluric current in the the X direction, and something that measures in the Y direction. And then you use that base station on the ground, just like you do with a magnetometer or with a differential GPS, to modify what the aircraft is receiving. And therefore, you can map essentially deep conductors. This is the KL1 kimberlite north of Sudbury in Canada. This is a ZTEM survey over it. Actually, no, I think this is a mobile MT, which is, they're just slightly different systems. And not only are we imaging in plan, but we can image it in section. You can see we've got good resistive granites on both sides, and an idea that this thing is a kimberlite in section, just like we do with EM. Just remember, no transmitter required. So becoming very, very popular. And in fact, mobile MT is new. It's only just hit Southern Africa. And of course, again, we can do the classic kind of 3D modeling that I was telling you about. In this case, this is down to 800 meters, and this is done just in Geosoft. So things are heading our way in 3D in a big way. Ground penetrating radar, I'm going to cover in 5 minutes because I'm so running out of time. But essentially, we're just looking for reflectors. Again, it's an electromagnetic technique. The reflectors look parabolic, like you can see in this image over here, but we migrate them to get rid of this time adjustment over here, and we get horizontal layers. And we get, what we're looking for is deep seeing geological information at 40 megahertz. None of the shallow stuff that maps roads and pipes. We want to go under 100 megahertz down to 40. So you have a long antenna, 2 to 3 meters long, and you can carry it. It's air coupled, and you want to work in rough terrain. So that's what we're looking for when it comes to kimberlites and alluvials. This is what we want to be able to do. This is really very rare to see something like this, but this is down to 70 meters that we are mapping the edge of the basin. We're mapping sediments in the basin. We're mapping an incredible amount of information. Don't get your hopes up. This is only on very rare occasions that we see stuff like this. Here's a real life survey done by Mike Shaw for diamond alluvials using our equipment. He did this himself. This is the Gobosh River Valley in the Cape. He wasn't actually looking for alluvials right here. He was just testing it. That's what the river looks like. And you can see that here is the base of the river channel here. Get all this muck on surface, the reflectors close to surface, related to ground effect, etc. But you can clearly see down at 10 meters, down to 15 meters there, the base of the Gobosh River channel, and that's the rising bedrock surface there. This is a river channel that is seen underneath Kalahari sand. This is an alluvial diamond study, again done by Mike. And I think this is fantastic because it's done under sand, and you can see the channel over here quite clearly. So we are starting to get somewhere with deep seeing antennas in radar. And we're starting to see through Kalahari sand. And in fact, we believe that we were seeing down to approximately 10 meters over here. Again done by Mike. This paleo channel is down at 10 meters depth. And this is over a large area. So this is 300 meters wide, the section you're looking at here. So that's 200 meters long, 20 meters deep, that entire gray section. And there's 5 meters of sand on top. And you can see that as long as you're not looking at a small area where you don't know what's going on, once you put this all together over hundreds of meters, you can see, in fact, you are mapping a paleo channel, which is very nice. Thanks to Mike Shaw for that. And a mafic sill, also buried under sand. I'm just showing you this section here in the bottom gray image. So take in these two red lines, and I've blown it up. And down here, you can see we're going along beneath the sand, 7 meters beneath sand. And suddenly we get these reflectors coming down to 12 meters here. And that's a mafic soil, which we believe to be diamond bearing underneath Kalahari sand. So ground penetrating radar, no, it cannot be used on a drone unless the drone is like a foot above the ground. We still don't have GPR that can couple in the air for meters. And just quickly in the last 5 minutes, stuff we can do with geophysical logging. In kimberlite pipes, this is some work I was involved with De Beers many, many years ago. And guys like Bill who are watching this will remember it well. Essentially, you throw probes down a hole in a kimberlite pipe, and you measure these things: density, porosity, magsus, gamma, and neutron porosity, resistivity. You measure all of those things up on surface by throwing the probe down the hole and slowly bringing it up. It measures them in the sidewall of the hole. And essentially, you can typify the types of kimberlite and the types of xenolith you have in the pipe. This is neutron counts on the y-axis and gamma counts on the x-axis on a log scale. And we start to typify what sandstone's response is, what this basalt response is, what that is, and also all these different facies of kimberlite. How do we do that? I'm going to show you how. This is what the result is like. Down the hole, 3 different holes, drilled close to each other for comparison. Got superb results, 3 different holes giving a very, very similar look at a kimberlite pipe. The top 80 meters, the green stuff is kimberlite. There's a basalt block in the kimberlite. So this is a scale of 0 to 100% across each hole here, i.e. there's 90% kimberlite where you see it green, 10% basalt where it's got a bit of red, and then where it's all red, that's 100% basalt. So for 80 meters, we're going through kimberlite, and then suddenly you hit basalt. Down here, we hit sandstone. Down here, we hit a bit of mudstone. It's telling us exactly how much kimberlite we've got at any depth, 90%, 85%, 80%, etc., and how much xenolith material there is every 10 centimeters, essentially. So a very powerful tool to calculate the dilution or dilution in the kimberlite body. How do we do that?
3 to 4 minutes, Gavin.
Okay, well, I'm basically wrapping up. I just need another minute. And we do that by measuring all these tools down hole, and then we plot them, we cross-plot them. Resistivity against neutron. Here are all your xenoliths, pulls them out beautifully. The yellow one is sandstone, the pink, the magenta one is one kind of basalt, the blue one's another kind of basalt. And here are all your different kimberlite types. They vary in conductivity or resistivity. There's kimberlite 3, 4, 5, and 6. And we can then take these graphs, create a mixing line between here and xenoliths over there. So these are mudstones and basalts, and these are sandstones. And we create a mixing line, and we can unmix it. We can say when we have 400 counts per second of neutron, that's 100% basalt. When we have 900 counts per second neutron, that's 100% of this kimberlite, and we unmix that thing. That's how we create those percentages. And even more so, we do a ternary plot where I can tell you when you're 100% kimberlite 6, because density versus gamma is plotting in this zone, just like we do with minerals in solid solution series. Kimberlite 2, 100% of it has this density and that gamma count, and all your xenoliths over there. And therefore, come back to this plot over here, where we typify sandstone, mudstone, basalt. We start by typifying it in a known hole, and then we tell it, unmix it, and the software just unmixes it for us and shows us exactly what we've got down hole. So essentially, you are logging the hole, in this case an RC hole, so very difficult to log, no core. It's just from chips. It's telling you exactly what percentage you have of basalt and kimberlite at any one point. Essentially, that's what we do with these unmixing relationships. Thank you very much. That's the end of it.
Thank you very much, Gavin. That was a very good overview of a whole bouquet of products. I guess a lot of the stuff is pretty new. We've got time for maybe just one query. There's one question in the chat box. When do you see a time when you can do 5x5 kilometer magnetic surveys with a drone? Is that far off?
No, we're already doing them. We're doing much bigger surveys than that. We just survey them in blocks. So I can do any size survey. We can do, I think we're doing one now in Swaziland that is that size. It's at least 5x5. But what we do is we divide it up into blocks, line of sight blocks, and also radio link blocks. So you can't lose radio link with a drone. So you go up on a hill, you say, okay, how far can I see? And then you have this very clever software that you show it where you are, and it plots line of sight for you and everything, and then it draws a block for you. It comes in GeoSoft. It's called the drone. It's a drone module, and it tells you you can fly this block from this hill. So then the only difficult part is the processing. We need to merge those blocks seamlessly, and obviously there can be trouble there. But again, we fly tie lines. So you basically take the tie line and you do tie line living with those blocks. So we can do any size survey. It just once you get to a certain size, it becomes more economical to fly it with an aircraft rather than a drone.